This is the second last board of this chapter. The main theme on this board, I suppose, is we're shifting up a level of description about Turing machines. We're familiar so far with the idea of a very low-level, detailed, formal, so-called formal description of a Turing machine, which just spells out all the details, the complete transition function, all the states and so forth. But that's just too tedious in practice. It's rarely done. And then there's a second level that we've been talking about. It's more what Sipser calls the implementation level, and that's more uses English prose, and some, well, we'll talk a bit more in detail a bit later, future sessions, on a description of the states and the transition function, that kind of thing. And then there's the high-level description, which is what we will increasingly focus on, and tend to forget about the first two. So this newer, easier to use, I guess, third description of the high-level description. So we'll talk about that in future sessions. And another theme, I suppose, is we defocus from the Turing machine and we emphasize more what the Turing machine is actually doing. In other words, implementing algorithms. Now, Sipser doesn't really explicitly state what the ChurchTuringThesis is. It seems to be more implicit. He could have done, I thought, in my view, a more forceful job of stating what the ChurchTuringThesis is. But effectively, so this is more me talking now, because I just see in the text he barely does, well, in this chapter at least, he barely does it, even though the title of the chapter is the ChurchTuringThesis. What is that thesis? Well, effectively it's saying our intuitive notion of what an algorithm is that it's a Turing algorithm. Now, since all these models of computation, general purpose, programmable computation, they're all equivalent, like the Turing machine, the Post machine, Church's lambda calculus, and so on. They're all equivalent. They're all provably, well, has been proven, of course. They're all equivalent. So you could easily label the ChurchTuringThesis as just the Turing thesis or the Church thesis or whatever. Now, what is that thesis? Well, that these so-called algorithms, in a vague, woolly sense, are more strictly speaking Turing algorithms or Church algorithms. But we'll use the term Turing algorithms. In other words, a Turing algorithm is an algorithm that can be implemented on a Turing machine. Okay, and that's the thesis, that an algorithm is a Turing algorithm, effectively. Okay, so you define if an algorithm can be that has implications that an algorithm, if it can be implemented, if it can be found even, then a Turing machine can implement it. That's the thesis. But I had to go. You have to go to other books to see it spelled out as explicitly as that. So again, it's well, my growing cynicism of Sipser, because he did not spell it out the way other authors did, even though it's the chapter title, which is odd. Anyway, we're especially the next chapter, we're approaching this incredible idea that there are problems for which there is no algorithm. In other words, given the ChurchTuringThesis, there is no Turing algorithm. Okay, and that's a pretty amazing idea. And we've been talking about the Hilbert's 10th problem. Given a polynomial find an algorithm that will show, yes or no, whether that polynomial, as an equation, the polynomial equals 0, whether that equation, polynomial equation, has integral roots. A root, what's a root? It's just a set of, well, the integral root is a set of integers for each variable. So say your polynomial involves variables, say 3 of them, x, y, and z. Then to find an integral solution, or root in other words, of that polynomial equation, you would give integer values to x, y, and z, such that when you plug those values into your x, y, z polynomial, you get 0. Okay? So the task, the question number 10 of Hilbert's famous list of 23 from 1900 at the Paris International Congress for Mathematicians, International Congress for Mathematicians, or Mathematics, find an algorithm that would decide yes or no whether a given polynomial equation has integral roots. And later, quite a bit later, this guy, I'm not quite sure how to pronounce. I think maybe it's Serb because of this itch from the news. It's not a language I know. So I'm not quite sure how to pronounce this J. Is it a J sound or a Y sound, as in Spanish? I'm not sure. So anyway, guessing. Yuri Matijazovic, I guess, in 1970, nearly 3/4 of a century later, after Hilbert's posing the problem, eventually came out using other people's work, like Martin Davis. We will use his text just a minute. I'll definitely be teaching a course on this, on computability and unsolvability by Martin Davis. Publisher is Dover, so that'll be an M2, second year master's course. I've shown that book before. Okay. Hilary Putnam, don't be fooled, it's a male, although Hillary, you've probably heard of Hillary Clinton, potential future president of the US, first woman if she manages it. And Julia Robinson, female, that's rare amongst theoreticians of computer science. They're rare as hen's teeth. So anyway, these people did previous work on this kind of question, whether you can find algorithms, so Turing algorithms, that can resolve a certain question. And eventually, in 1970, Yuri Matijazovic showed that there is no such algorithm. So there's no solution. And therefore the question is unsolvable, and that would have profoundly shocked Turing, because it just didn't enter his head that there would not be an algorithm. That was a later consequence of the theory of computation that came out of the work of people like Turing, Church, Kleene, that's K-L-E-E-N-E, Post, and others. All right. So what did he do? Well, he actually showed there is no algorithm, right, that can test if a polynomial equation has integral roots. That was Hilbert's 10th problem. Now, so next chapter we will be developing techniques that will serve as the foundation, like the basis. So for proving this kind of thing, we'll understand better, having done chapter 4, how Matijazovic proved what he did, namely that there is no algorithm for this problem. Okay. In other words, that this particular problem and others are algorithmically unsolvable. And I put like four exclamation marks, because personally I find that notion's fascinating. That that you can actually prove that something is unsolvable, meaning there's no algorithm to do it. You actually prove that there's no algorithm to do that, given the problem. And now it's a whole industry. There's a huge number of theorists working on this kind of problem. You're trying to taking a particular problem and trying to prove one way or the other whether it can be solved algorithmically using some algorithm. Because it's important if it's known that a certain problem is unsolvable, then provably unsolvable, then you're just wasting your time trying to solve it. Right? So it saves effort. The collective enterprise to try to classify, if you like, problems into solvable, unsolvable, that kind of thing. Helps future researchers. They will not go trying to solve something when it's known, provably known, that it's unsolvable. Sort of common sense. Right? Okay, now we'll use a terminology that we'll keep using in the next two chapters, chapter 4 and 5, which, by the way, are not so large. I actually calculated roughly the number of pages for the next couple of chapters. So this one's around a bit over 20 odd pages. Chapter 4, decidability, decide, a Turing machine deciding or not, about 18 pages roughly.